Good morning and welcome back to Dr. Logic Awkwardly Does Logic. In this video, I'm going to give you a proof of the theorem that I stated in the previous video, namely that there are 14 distinct modalities in S4. We'll prove this using the reduction principles that we'd proved in earlier videos, but the basic idea is this. What we have to show is that each of the 14 are not reducible to each other. So for any pair of them, I need to be able to produce a model that makes one of them true and the other one false. That we will probably skate over because it's basically just model building. You've had lots of experience with that. The other side is that we have to show that any one of the modalities which is not one of these 14 is equivalent to it, i.e. can be reduced to it using the modal reduction principles. So that might seem like a very difficult task, given that there's infinitely many of these modalities, depending on how long we want to make them. And yet we need to show that they are all equivalent to one of these 14. But we can do this in a systematic fashion. So let's go ahead and do that now. Just to make things easier, I've already put the statement of the theorem up on the whiteboard. So the 14 distinct modalities are these 7, the positive ones, and their negations. We're only going to focus on the positive ones. The proofs for the negative ones can be done in exactly the same way. So I will leave that as an exercise for you. So as I said, first what we want to do is to look at how to take all of the ones that are not on this list and show that they can be reduced to ones on this list. So consider the 7 positive ones. What we need to do is look at what happens if we take one of them and add another modality to it. So consider the 0 case. So that is, I'll change my color so you can see what I'm doing. That's this one. This is where, that underline is just supposed to indicate nothing. So consider the 0 case where we have no modality. There are 2 possibilities. We can either add a box or add a diamond. So consider adding the box to it. Then the modality that we have is equivalence. Wow. I think something has happened with Zoom's whiteboard and it doesn't work as well as it used to. Apologies for the messy writing. Anyway, adding a box to it means that we have something that is equivalent to modality 2. The other option is consider adding diamond to the 0 case. The result is equivalent to the 3rd one. So if we start with the 0 case and we add another modality, we have something that is already in our list of distinct modalities. So we're good. Now, consider the single operator cases. So this is going to be the procedure that we do. We're going to look at modalities of string of length 0, modalities of length 1, 2, etc., and then ask what happens if we add a modality. So consider the single operator case. That is the box and the diamond. So these cases are already in the list, so we know that they are distinct. Now, if we prefix box to, well, here, what I'm going to do is we have box and we have diamond. So there's 2 possibilities. I can either put a box on the front of both, or I can put a diamond on the front of both. Now, if I have diamond box, this is already in the list. This is number 5. If I have box diamond, this is also already in the list. This is number 4. So what we need to do is show that these are either in the list or equivalent to something in the list. And one of our S4 reduction principles says, if you have 2 boxes, you can always reduce it down to 1 box. And if you have 2 diamonds, you can always reduce it down to 1 diamond, which means that this case is actually equivalent to something already in the list. And this case is also already equivalent to something in the list. this is the strategy that we'll then use for the next cases. So consider writing things in the right place. So consider the 2 operator cases. That is when we have 4 or 5, because we don't need to consider the 2 operator cases, box, box, and diamond, diamond, because these are reducible to 1 operator cases, which we've already considered. So we have either box, diamond, or we have diamond, box. These are the 2 possibilities. Again, we can ask what happens if we add another modality to them. So either we can add box to both of them, or we can add diamond to both of them. And now you should be able to see how this is going to go. This one is equivalent to something already in the list, i.e. number 6. This one is also equivalent to something in the list, i.e. number 7. This one is not in the list already, but we already know from the 1 operator case that 2 boxes can reduce to 1 box. So this becomes box, diamond, and this is in the list. This is number 4. And same here, our 2 diamonds can reduce to 1 diamond, and diamond, box is already in the list. That's number 5. So we've looked at all of the possible 2 operator cases and added 1 more operator to them and shown that the result is either in the list or equivalent to something in the list. So finally, we've got the 3 operator cases, and I hope I can get them to fit in here. So the 3 operator cases are 6 and 7. So box, diamond, box, and diamond, box, diamond. Now we don't have to consider any of the other strings of 3 operators, because we already know by what we've just seen in the 2 operator case that this will reduce back down to one of the 2 operator ones. So these are the 3 operator cases we need to consider. We can either put boxes on the front of them, or we can put diamonds on the front of them. And then we need to show that the results are either already in the list or equivalent to things in the list. Now, none of these are in the list because they're all 4 operator strings, and we only have in our list of 14 maximal 3 operators. So we need to show that each of these is going to be equivalent to something in the list. Now, in this case and this case, we already know what's going to happen. This gets reduced down to 1 box, and then is going to be equivalent to number 6 in this case. This gets reduced down to 1 diamond and becomes equivalent to number 7. But now we've got these: diamond, box, and box, diamond, box, diamond. This is where another one of our reduction principles comes in. It says if you have 2 pairs of alternating modalities, you can reduce down to 1 pair. So box, diamond, becomes just box, diamond, and that's number 4. And then diamond, box gets reduced down to just diamond, box, and that is number 5. So we've shown that the 3 operator cases, if we extend them with 1 more operator, all reduce down to something that we already have, either a 2 operator string or a 3 operator string. So now this is as far as we need to go, because if we consider any modal operator that has 5 or more modalities in it, any string of modalities of 5 or greater, it will have within it some string of either 2 modalities or 3 modalities that we can already reduce. So we don't have to consider any more cases, because all of those cases are already subsumed under the reductions that we have already done. So if you have a 5-length modality, there will be at least one 2-length modality in it that you can reduce, or there will be a 4-length modality in it that you can reduce, and that will bring you back down to one of these other cases. So as I said, this is half of it. This is showing that every single bigger modality, every single other modality that you could generate is going to be equivalent to something in one of these lists. The other half of the proof, which is the part I'm just going to wave and leave as an exercise to you, is to show that each one of these are in fact distinct from each other. All you would need to do is come up with some counter model where for any pair, you can make one of them true, but the other one false. So I will just very briefly show, let's make P, i.e. the zero operator, true, and possibly P false. Well, single point dead end world, where P is true, then the 0P is true, but possibly P is false because this world can't see any world where P is true. Something more complex, let's consider, necessarily, possibly, necessarily P, and possibly necessary P. We can do the same sort of technique. Single point dead end world, this is going to be true because everything is necessary at a dead end world. This is going to be false because nothing is possible at a dead end world. And similarly easy counter models can be made to show that any pair of these other modalities is non-equivalent with each other. So there you go. It's sort of a long proof, but it's not a difficult one. You just have to kind of understand how the parts fit together in order to show that in order to understand that this proof does show what we want to show. So we'll say a little bit more about implications between modalities and equivalences in S4, because the structure of implication between different iterated modalities or just general strings of modalities is something quite interesting. And you can end up using this to say quite a bit about the expressive power of a language, the sorts of modal concepts that you can express in it, and things like that. But we'll take care of that in the next video. Until then, take care. Cheers.